Welcome to this explainer. Today, we're unpacking a massive, truly fascinating engineering feat. We're going to look at exactly how the Uber Delivery Data Solutions team conquered an absolute nightmare of an infrastructure problem, and they did it without dropping a single query. Seriously, if you've ever dealt with a system architecture that has just completely outgrown its original design, you're going to love this deep dive. It's basically a masterclass in how to fix an airplane mid-flight without turning off the engines. To really appreciate this, you have to wrap your head around the sheer scale we're talking about here. Just picture 10 petabytes of data spread across 16,000 distinct datasets, and it's all trapped inside one failing, centralized monolithic database. Talk about putting all your incredibly heavy eggs in one very fragile basket. And this wasn't just old, archived, dusty data sitting in a corner. This was highly active, dynamic information being constantly read from and written to by thousands of downstream consumers. The dependency graph was incredibly dense, and frankly, it was becoming a very serious problem. So to understand how they safely dismantled this giant, we're going to follow this roadmap. First, outgrowing the monolith. Second, the zero downtime challenge. Then, the pointer strategy, the migration machinery, and finally, the petabyte payoff. All right, let's jump right into part one. Outgrowing the monolith, this is where scale basically turns into a liability. Now, in the beginning, this massive single bucket setup was actually incredibly convenient for onboarding and discovery. But as Uber scaled up, the monolith literally started cracking under the pressure. Because everything lived in one namespace. If a single team accidentally corrupted some metadata, it could cascade and crash Tier 1 workloads. Engineers call those shared fate outages, and they are brutal. On top of that, you had terrible resource contention, the classic noisy neighbor problem, right? An ad hoc query from one team would suddenly tank the query latency for everyone else. Plus, every little operational task had to flow through one central team, creating massive bottlenecks. And maybe most dangerously, this giant bucket granted broad read and write permissions across the board. That is a huge security risk and completely violates least privilege principles. Moving on to part two, the zero downtime challenge, or why a seamless transition was the only option. Look, usually to fix a broken system, you just turn it off, fix it, and turn it back on. But think about what this failing monolith was actually powering. We're talking about the machine learning algorithms that dictate Uber Eats dynamic pricing and recommendations in real time. We're talking merchant analytics generating financial payouts and Tier 1 reporting that's absolutely required for compliance. You couldn't just switch this database off, even for an hour. If you did, you'd break dynamic pricing, halt merchant payouts, and blind the executive dashboards. The migration had to be absolutely perfectly seamless. Which brings us to part three, the pointer strategy. It's time to update the map. So here's the million-dollar question. How do you move 10 petabytes of highly active, business-critical data without anyone noticing? Well, the engineering team realized something crucial. They didn't actually need to move all the data immediately. Instead, they leaned on a magic weapon called the Hive Metastore, or HMS. I want you to think of the HMS like a massive address book. When a query asks where data lives, the HMS points it to the physical file location on the disk. So instead of physically lifting and moving a giant house, which takes forever and causes massive disruption, you simply build a new house, move the contents once, and then instantly update the address in the book. And this right here is the real eureka moment. They take the original dataset, create a new decentralized location, and copy the physical data over exactly one time. Then comes the magic part. Pointer manipulation. They update the Hive Metastore pointer in a split second. From that exact millisecond forward, any new read or write request naturally just flows to the new location. They achieved a totally seamless transition without having to constantly run heavy, duplicate pipelines for petabytes of data. Okay, part four, the migration machinery. Because safely pulling this off requires automating absolute precision. Safely updating pointers across 16,000 distinct datasets is no joke. It requires an army of automated robots. The whole thing kicks off with the Bootstrap migrator. Relying on Apache Spark, which is a massive distributed computing engine, it spreads the copying workload out so there are zero bottlenecks. But here's the best part. Before any pointers are actually flipped, it runs incredibly strict checksums. It verifies that every single byte of the new location perfectly matches the old one. If anything changes during the copy, say a partition gets deleted or backfilled, the migrator immediately catches it, fails the check, and reruns the process. They guaranteed 100% data quality before moving an inch. But wait, what about the active writes happening during this transition phase? To keep both the old and new locations strictly in sync, they built a bulletproof, bi-directional safety net. They paired an instant real-time Apache Flink stream that listens for immediate metadata updates, with a secondary batch synchronizer acting as a bi-hourly sweep. So if a real-time message drops for whatever reason, the batch sweep catches a discrepancy 2 hours later and fixes it. It's a highly resilient setup that absolutely guarantees eventual consistency. And finally, part 5, the petabyte payoff. Let's look at the ultimate results. After orchestrating this incredibly complex ballet of data and metadata, the numbers really speak for themselves. Behind the scenes, those synchronizer robots executed over 7 million individual metadata syncs. 7 million. That's 7 million silent adjustments happening in the background to ensure operations remained flawlessly uninterrupted for Uber's downstream consumers. And honestly, here's the kicker. By manipulating the map rather than endlessly hoarding duplicate territory, and by carefully cleaning up stale datasets during the migration, Uber didn't just spend money to fix a problem. They actually saved a massive 1 petabyte of physical disk space. That's a pure, massive byproduct of this entire operation. But beyond those massive storage cost savings, the architectural wins are just staggering. They permanently solved the noisy neighbor problem. That dangerous, bloated monolith? Gone, replaced with decentralized, highly secure, independently scalable databases. Now every single domain has fine-tuned capacities. They finally achieved strict access control list compliance for least privilege security. And the best part? If one team's metadata gets corrupted today, the blast radius is completely isolated. Tier 1 workloads are completely safe. This whole project is just a masterclass in platform engineering. As you look at your own engineering challenges, whether they're in software, ops, or even organizational structure, ask yourself this: what massive bottlenecks are you facing right now that could be solved simply by updating the map instead of painfully moving the territory? Sometimes the absolute smartest, most efficient way to move a mountain is just to redraw the map. Thank you so much for joining me for this explainer, and keep building smart.